So we saw one divide and conquer algorithm that was new, which was to count inversions, which was a version of merge sort in which we also kept track of how many times we pulled elements from the right hand side. Now let's look at a completely different problem, but one that we promised we would solve at the beginning of the course. So if you remember, one of the motivating examples for looking for efficient algorithms was this video game. So we said that there are several objects on the screen, and perhaps one of the basic steps that the video game has to perform every time there is a change in the situation is to find the closest pair of objects on the screen. So we said that this can be done by brute force by looking at every pair of objects on the screen, computing the distance and then computing the minimum amongst these. But this would take order n squared time, and we promised that we would find an algorithm which did something better than this. So what we are going to report now is this clever algorithm which is going to take n log n time, right? And this clever algorithm is going to use divide and conquer. So let's set up this problem more formally than in this video game context. So what we have are a collection of points, and we want to find the nearest or closest pair of points. So what is a point? A point is just a point in 2 dimensions. So it has an x coordinate and a y coordinate. So every point P has an x part and a y part. This is just a normal point in 2D. So if I give you 2 points x1 and y1, x1, y1 and x2, y2, right? So you know that by Pythagoras formula you know this distance, right? So it is the square root of the length of the hypotenuse, right? So I mean it's the length of the hypotenuse, which is the square root of the squares of the other side. So this is just what is called the Euclidean distance. So we are just going to use this distance to determine which pair of points is closest to each other. So we are going to make one small assumption. So we are going to assume that there are no 2 points which have the same x coordinate. In the sequence of n points, there is x1 to xn and y1 to yn. So we have n x coordinates, n y coordinates. We are going to assume that no 2 points lie on the same vertical line, no 2 points lie on the same horizontal line. Now this may look like a serious restriction, but imagine that you have such a situation that you have 2 points which lie on the same vertical line. You just rotate the points by a small degree, right? You just rotate them by a little bit. Now they are no longer in the same vertical. So it's just a little bit of change of orientation. So you just perturb the points slightly by just rotating them. The distances will not change, right? You can check that for yourself. If you rotate points, the points relative to each other do not change. Their distance with respect to the x or y axis may change, but the distance relative to each other doesn't change. If I just rotate something, they all stay with the same relative distance. So I can assume that and solve it. Now if you are not happy with that, then you can also take the algorithm that we are going to look at, and you can actually perturb it. The algorithm can be made more sophisticated to take care of this, but it's convenient to assume that these points actually have distinct x and y coordinates. So as before with every such problem, right, we said that in the video game case, you can always do it by brute force. You can take every pair of points pi, pj, and you can compute the distance and then take the minimum of these. But this, the problem is, will take time n squared. If there are n points, I have to compute distances for n into n minus 1 by 2 pairs of points, and I want to do something better than that. So let's see why this should at all be possible. I mean, why is it possible to even imagine that there is something better than n squared? So let's look at the same problem but in 1 dimension. Now in 1 dimension also, right, the brute force algorithm. So what does 1 dimension mean? 1 dimension means that I don't have a y coordinate, I only have x coordinate. So everything is lying along a horizontal line, and I have these points like this, right? And the distance between 2 points is just the difference between the 2 x values, and because they could be one bigger, one smaller. So remember, in the other case, in the 2-dimensional case, we took the square, so we made it positive and then took the square root, the positive square root. So the distance is always positive. Now here, if this was say -3 and this was -2, then you have to be a little careful about how you measure the distance. The distance should be +1 and not -1, right? So we will typically take the absolute value of the difference between the 2 points as the distance. So once again, the naive thing would be to just take this absolute value for every pair of points. So again, you have an n squared algorithm, right? If you do it even for 1 dimension, the brute force algorithm doesn't, because it's 1 dimension, it doesn't change. It's still an n squared algorithm. But we have a much cleverer algorithm for 1 dimension, which is very simple. You just sort the points, right? So now if you sort the points, so these are, if I am now looking at points in sorted order, then where are the neighbors of this point? Okay, so where are the neighbors of this point? Well, it could be this point and it could be this point. it is certainly not the point which is 2 steps away, right? Because no point which is 2 steps away can be closer than some point which is 1 step away in this sorted sequence. So the nearest points to any point P in the sorted sequence are its neighbors before and after. So then all I need to do is take the sorted sequence, right, and compare the gaps between the points. Nothing else matters. But the number of gaps is n minus 1, right? I have n points, so I have a gap between the first and second and third and so on. So I can do one scan, and in order n time I can scan all the points to find the minimum separation between adjacent points. So therefore the problem has been reduced from n squared to n log n, which is the time it takes to sort the points. So this is our motivation for looking for a better algorithm than n squared in 2 dimensions. If I can do it in n log n in 1 dimension, can I do something cleverer than n squared in 2 dimensions? So since we are looking at divide and conquer, it's logical that we are going to somehow use divide and conquer to do this. So what does it mean to divide these points? Well, remember that our usual naive way of doing divide and conquer is to divide the subset into 2 parts, the first part and the second part. We take a list, we take the first half and the second half. So here geometrically, what it means is that we have a bunch of points, right? So we will somehow divide it, it doesn't matter whether we do it horizontally, but just geometrically we will say take everything to the left of the red line, take everything to the right of the red line, such that it's roughly half on both sides. Then divide will say recursively find the solution within each half. So I now know the shortest distance to the left of the red line, I know the closest pair of points to the right of the red line. But the problem is that I could have some points which are very close to the red line, which are in different halves. So they might be very far away from the corresponding nearest points on their side, but they are very close to each other, but they are in the different sets. One is in the left set, one is in the right set. So just like earlier we had to count inversions from between the left and the right set, here we also have to compare distances across this boundary. Distances within one boundary, within one of the 2 groups gets done recursively, but distances across the boundary is our merge step. So we have to do the merging. So how do we do that efficiently? So that will be the crux of the problem. So let's see how to do that. So what we are going to do is we are going to add some structure to the points that we are given. So we are given these n points, right? So this is a set of n points like the ones on the right, which are kind of randomly scattered. So these are something like 20 points are there, right? But now I am going to do 2 sorts. So I am going to list out these points in this direction. So this will be 1, this will be 2, this will be 3, this will be 4, 5 and so on. And I am also going to list out the points in this direction, right? So this will be 1, this will be 2, this will be 3, this will be 4 and so on. So this green list will be the Px list, right? So this is a listing of the points in order of x coordinate, and this is a listing of the point in the order of y coordinate. So I am going to first do this for the initial list of points. I am going to first sort the initial list of points by x and y, and then I am going to always apply my recursive algorithm assuming that the list of points that I am given has this property that it has a x sorted component and a y sorted component. I mean, notice that px and py, I am not dividing, I am just presenting to you p in 2 different orders, in the x order and the y order, right? So px has all the points in p. Py has all the points in P. It's just that Px is sorted by x and Py is sorted by y. And as we go along, we don't want to sort again and again. So we have to make sure that when we do this divide, we can extract the sorted things for the 2 halves easily. So this is the divide step. I take a line such that I have roughly half the points on the left. How do I know that? Well, I know that Px has the x coordinates in sorted order. So I can walk up halfway through Px, right? If I walk up halfway through Px, then at the middle of Px, the median point of the list Px tells me where to draw this line, right? Everything beyond that is in the right, everything before that is in the left. So this splits it into 2 parts, let me call them Q and R, right? So if this was n points, these were both n by 2, right? So now what we have to do is we have to take this Px, Py and divide each of these Q into Qx, Qy and Rx, Ry, because to continue this recursion, I need to solve the problem with a given set of points having an x sorted version and a y sorted version, right? and I don't want to sort again. So this n log n I have done once, I don't want to do it again. So how do I get these sets qx, qy? So qx is q sorted by x, qy is q sorted by y, and so on for r. So the x sorting is easy, right? Because I just go from left to right, and I know where this red line was drawn. So everything whose x coordinate is before the red line will be the first half of px, and then everything which is after the red line will be the second half of px. So splitting px into qx and rx is just a matter of splitting, like in merge sort, splitting px into two halves. The first half is qx, second half is rx. Now the problem is that it's not so easy to split y, because I cannot split y this way, because if I split the y's this way, right, then some of the points above are on the left, some of the points above are on the right. Similarly, some of the points below are on the left, some of the points below are on the right. So I can't just do the same thing for y, right. So for y I cannot just say that the first half of py is qy and the second half is, it's not that way. So I need to split y more cleverly. So what I need to do is go through y from here to there and decide for every point should it be left or right. So how do I know whether it's left or right? It depends on the x coordinate of that point. But what do I know? I know that the red line divides the two. So for instance, when I am doing the split, I can either pick up the largest x value in q or the smallest x value in r and use that as my boundary, right. So let, for example, xr be the smallest, so this is the one, right. So this is the smallest, that is the leftmost point in the right set. So now as I go up, what I do is I check this and I say where it is with respect to this. It says, oh, it is bigger than that. So then I will say, okay, then this will go to ry. Similarly, this will go to ry. Now I come to this point and I say, where is it with respect to that? It will say, oh, its x value is smaller than this xr. Then this must go to qy. This must go to qy, right. So in one scan going up, by looking, so I am looking, the y coordinates are sorted. So I am doing it in y order. So the output is coming in y order. This is important, right. I don't have sort again. I am getting the values, it's like an unmerge, right. So in merge we take two sorted things and produce a sorted thing. Now I am taking a sorted sequence and dividing it into two groups, but the two groups I am creating are individually in sorted order because I am building them up in the same sequence. So qy and ry are being constructed by scanning py in sorted order. So they are themselves in sorted order, right. So if you accept this, then I just do this. For every p in py that is in sequence, if the x coordinate of p is less than xr, I put it in qy. If it is at least xr or more, I put it in ry. And this happens in one scan, and in one scan notice the point is that qy and these things are sorted, right. I don't have to sort them again. Now these are clearly sorted because they are the first and second halves of a sorted list, but these are being built up in sorted order, so they are also sorted. So therefore in one left to right scan I have split px into qx and rx, and in one bottom to top scan I have cleverly split py into qy and ry. So I now have on this side qx and qy, and on this side I have rx and ry. So now I can tell these guys to go and do their job recursively because they have the same structure as the original problem, right. And the key thing is that this whole splitting operation, drawing the line and splitting it into two parts and making sure that each part is decomposed into the x and y part, everything was done in linear time, right. This whole thing was done in 2 or 3 scans. So order n time is all I did. This is crucial because we know that if you spend more than order n time in breaking up things, then your recurrence is not going to work properly. So in order n time I have done the dividing. So now I want to do the actual recursive algorithm. So what I want to do is compute the closest pair for the original set which is given to me with this decomposition px, py sorted by x and sorted by y. It's not a decomposition but two presentations. So px is all of p, py is all of p, but one is sorted by x, one is sorted by y. So then I will recursively, I will split it so that I here have qx, qy and rx, ry. This is what we just showed, you can do it in ordered n time, right. And we will recursively compute the closest pair of both of these sets. So now I know, for instance, maybe that this is the closest pair here and this is the closest pair here, okay. So the problem is how to combine these recursive solutions, because in the process of doing this there may be some closest pair across this boundary, okay. So let's look at this combining the solution, and that's really the clever and very tricky part of this divide and conquer. So remember that we have found recursively the smallest distance on the right and the smallest distance on the left. So the dq is the smallest distance in the q set, dr is the smallest distance in the r set. So let me use delta, okay, this Greek letter delta to denote the smaller of these two. So it's the minimum of these two values. So my goal is to find out whether there is something which crosses this boundary which is distance less than delta, right. I know that within each of these two halves I have nothing which is closer than delta. Delta is the smallest I see between the left and the right combined. So what can we do with this delta? Okay. So what we can do is we can focus our attention on this band which is within distance delta of the separator, right. So this distance here is delta. So I draw a line which is delta to the left of the separator and I draw a line which is delta to the right of the separator. So this delta band, so it's delta plus delta, so it's 2 delta wide, okay. The claim is that if I want to look for these boundary crossing points, if I want to look for a point here and a point here, then I should look only within this band. Why? Because if I have a point which is outside this band, right, and it must cross this band to go to some point other than there, it must first cross the band. So band is already delta wide. Now this is outside the band, so it is more than delta. So the distance to the other side cannot be less than delta. So anything which is more than delta I am not interested in because I already have a delta solution here, right. So no pair outside this band can be closer than delta. So therefore it is sufficient to focus on those points which lie inside the band. Okay, but there is no reason in principle why everything cannot lie inside the band. All of these points could lie inside the band. I mean, I could have a different pathological picture in which I have these bands like this, right, and everything is here. This could be the picture of Q and R, right. So in principle there is nothing to prevent this. So why is it that comparing the band across this band is going to be more efficient or somewhat efficient as compared to just comparing everything in Q with everything in R, because everything in Q and R could actually lie inside this band. So what we will see is that this is not possible, and this is really remarkable. It says that in this band there can only be very few points. So now I am focusing on the band. So this is that band. I am only looking at points inside the band, right. So the left hand side is Q as before, the right hand side is R as before. And now this is my band. So I have delta here and I also have a corresponding delta on the other side. So what I have done is I have taken this band and I have further subdivided it into these boxes of side half delta, right. So each box, this is delta, 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 right. So I have taken each thing and I have divided it into these smaller squares of half delta. So this is just to visualize, right. So I have basically taken the band in some sense and divided it into 4 strips. So it was 2 strips of delta. I have now made it 4 strips of half delta and I have cut it across in half delta squares. So as we said, some of the points from our old set lie inside this band, so they are lying here, for example. Okay. But many of the points are lying outside, and those points I don't care about because they cannot contribute to my best solution. Now the first and the most crucial observation is that actually these boxes cannot hold more than 1 point each. So we were earlier asking whether there can be lots of points inside this band. In fact, can all the points be there, right? But the first observation is that you cannot have, so these points have to be somewhat separated. Now why is that? Because if you look at 2 points within a box, what is the furthest they can be? The furthest they can be is to be at opposite corners of the box, right? So if they are at opposite corners of the box, then the distance that separates them is the diagonal of the box. But remember that each box is entirely on one side, either it's on the left or on the right. So if there are 2 points which are within one box, they are either both in Q or they are both in R, so their distance has to be at least delta. But this diagonal is actually smaller than delta. If you just calculate this, use Pythagoras theorem, this is delta divided by square root of 2. So square root of 2 is more than 1, it's 1.4, right. So this is 1 upon 1.4 times delta. So this is something which is smaller than delta, right. So if there were 2 points inside a square, then they would be less than delta. But we can't have on either side of the separator any 2 points which are closer than delta, because delta is the closest possible distance for any 2 points on the same side of the separator. So that means that these boxes all contain at most 1 point each. So now we are looking at points across these boundaries. So supposing I have a point here, right, and now I want to find a point which is very close to this point but on the other side. So remember that this is delta, right. So perhaps this is just inside this side and maybe this is just outside that side. So this is about the closest I can get while being far away in terms of the boxes. Right. So the point is that if I start in this row, right, technically I cannot go more than 3 rows above. Right. I cannot even reach the third row, but this is just to be safe. Now let's look at our points in the y direction. So we have points which are sorted in this direction. Right. So where do they lie? So I could have a point just above this first point. So let me write a 1 here. I could have a point which is very close to this one point, but it might be here. But then I can't have anything else on that side. So another point which is still in the same row must be somewhere else. So there may be 3 other points which are bigger than 1 in the same row, but they must all lie in different boxes. So now if I have a 5th point which is bigger than 1, right, a 5th point, the 4 points bigger than 1, then it must lie in the row above. Right. So I could have 5, 6, 7, 8. Now if I have one more point, it must lie one more row above. Right. So basically the worst case is that this point was actually here, right, and then I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15, right. So I have to check between 1 and 16. So there is one point which is 15 points away in the y direction, but it must lie within this 4 by 4 neighborhood of boxes. So if I look at the box in which the point I am examining sits, right, then any point which, so remember I'm always doing this in ascending order. So if this point is close to a point which is smaller than this in the y direction, that point would have found this as a neighbor. So I'm starting with the smallest y and going upwards, right. So therefore when I'm looking upwards, I'm saying that if I want to look for points which are within delta, they cannot be more than outside this 4 by 4 box compared to where my point is. And in the 4 by 4 box there are 16 boxes, they can be at most 16 points. So therefore I need to compare this one point against at most 15 other points. It's a fixed number, it doesn't depend how many points there are to start with. I cannot have more than 15 candidates for any given point to compare. So this is the reason why now this comparison becomes efficient, because I have to compare each point with a constant number of points, not a number of points which is proportional to the total number. So essentially what I need to do is first determine which points are inside this band in sorted y order. So I do the same trick as we did when we split the thing. So remember when we split the thing, we looked at py, right, and we decided whether to put something in qy or in sy, in ry, depending on the x coordinate. Now what I can do is I can go through qy, I can do a kind of clever merge basically. I go through qy and ry, I take the smaller y coordinate, I check if the x coordinate lies in the band. What is the band? The band is the separator plus minus delta. So if the x coordinate lies in the separator plus minus delta x, then I will put it into sy. If it doesn't, I throw it away. Then I will pick up the next smallest y coordinate between q and r. So I am merging these two and then I filter. So I want x to lie between this. So from qi and ry I can generate this set sy, which is all the points in sorted order which lie inside this band of interest. And now once I've got the points inside this band of interest, I take the first point and I compare it to the next 15 points, because those are the only ones which can lie within delta of this. If none of them are there, then I take the second point and compare it to the next 15 points. I take the third point, compare it. So for every point in sy, I'm comparing it to at most 15 more points. So I'm doing 15 times n work. So basically it's order n work, right? So all these things now are again, it's a linear scan, right? It's some order n work to scan this. Now this is a kind of very, I would say, conservative thing. You can actually do a tighter calculation than this. But this loose calculation is very clearly correct, that you don't ever find a point which is more than 15 points away in the y direction, okay, regardless of the coordinate, We are not talking about we are saying in the sequence, if I am looking at x1, then I only have to look up to x16. If I am looking at x3, I only have to look up to x18 and so on. Right? So this is what we do. So it's a little tedious to write this whole thing in Python and fit it on a slide. So let me just write it in pseudocode to explain what we did. So you are computing the closest pair of a set P, but we assume that set P is given to us in two sorted lists. Right? There are two sorted lists, each of which has all the points in P, but one is sorted by x coordinate, one is sorted by y coordinate. So first of all, if it's a very small list, right, if it's up to 3, I will just do it brute force. I will just compute every pair in that. So there are 3 points. I will compare all the 3 pairwise distances, 1 to 2, 2 to 3, 1 to 3, and report the closest pair and the distance of that. Right. So I will just do it by brute force. If it is 4 or more, then it makes sense to divide, because then I will have halves which are at least 2, right. So I will construct, as we said before, qx, qy, rx, ry by finding the midpoint, right. So I would remember that this is sorted, so I don't have to sort again. So I will walk up px halfway and call that qx. The remaining part I will put in rx. I will remember the extreme coordinate of px and rx, and using that qx and rx extreme coordinate, I will walk up py and split it as qy and ry by deciding which side each point goes to. Now I will recursively find the solution for these two halves, right. So it will report back to me the nearest pair of points. So q1 and q2 are the points, r1 and r2 are the points, and dq is the distance between these two nearest points in q, and dr is the distance between the nearest points there, right. So now once I have this, remember that implicitly this delta, we needed the delta only for the proof, we don't need it for the code. Delta is the minimum of this dq and dr. So using that delta, I will construct this sy, right. I will look for all the points whose x coordinate lies between the separator minus delta to separator plus delta, and put it into sy in ascending order in y coordinate. And now I will do this linear scan every point with the next 15 points in order to find out the smallest separation within this band. So now I have 3 candidates. I have the left hand side candidate, which gave me dq, the right hand side candidate, which gives me dr, and this band provides a third possibility, saying this is the smallest distance within this band for points which could be on either side. So I take, depending on which of them is minimum, right, dq, dr and ds, these 3 distance, whichever is minimum, I use that as my answer, and I say, okay, this is the pair of points overall which has the minimum distance, and here is the distance, right. So this is my algorithm. So if you want to analyze this, there is an initial step which is outside this function, which is the sorting, right. So initially I have to do some n log n work to sort this, but it will turn out the whole thing is n log n, so it does not matter. So now I have a recursive algorithm, and all this stuff, right, took O(n) time. So in order n time, I was able to split px, py into these 4 lists, qx, rx and qy, ry. Similarly, in the combine step, I was able to combine this by constructing sy in linear time and doing a linear scan on s. So all the splitting and combining, all the work of generating the recursive step and using the solution from the recursive step is order n. And of course, now I have to do 2 times the work for the half. So the recurrence is just solve the problem for half the size of points twice, once for the left, once for the right, and do this order n work to split and combine. So this is exactly the recurrence from merge sort, because we have a trivial case where we will just do some constant amount of work in return, right. So therefore this whole thing is n log n. So this part is n log n, and then we also have an extra initial step of sorting the p to start with, because that does not come to us sorted. So that is an extra n log n, but so we do n log n twice, so it is not a problem. So we do it in n log n time. So therefore, as promised, that video game problem, where we wanted to keep track of the nearest pair of objects on a screen dynamically, can actually be solved in n log n time using this clever divide and conquer technique.